Alright, so this lecture is all about oxidation numbers. And so before we get into the oxidation numbers themselves, I want to kind of explain why why we had to learn how to do this. And the reason why is when we look at a chemical equation and we want to decide whether it's an oxidation reduction reaction, we can't always rely on the charges of the ions because there's oxidation reduction reactions where there really are no ions, yet there are electrons essentially being transferred, between atoms, and there is a change in the oxidation, what's called the oxidation state of those atoms. So what we're going to go through is an accounting system. It's totally a convention that chemists use in order to track the flow of these electrons. And what will happen is in a chemical reaction, what we're working up to in a chemical reaction, we'll assign every atom in that chemical reaction an oxidation number. And then we'll look to see if that oxidation number changes as it goes from reactants to products. If it does, then if there's an increase in the oxidation number, we say that the atom was oxidized in the reaction. If there's a decrease in the oxidation number, then we say it's going to be reduced. A funny notation that we use, or terms that we use, are reducing agent and oxidizing agent. A reducing agent in a reaction is the atom that reduces some other atom, which means that the atom that's doing the reduction is itself oxidized. So the oxidized atom is what we call the reducing agent, or the compound that the atom is in is called the reducing agent. And the compound that contains the element that's reduced, in effect, is oxidizing some other atom, and so we call the compound with the atom that's reduced in it the oxidizing agent. Confusing, I know, but these are two terms that you need to know when people talk about redox reactions. We talk about something being a very good reducing agent. What that means is that it's very easily oxidized, and if something's a great oxidizing agent, it means that it's very easily reduced. Okay, so what are these rules for determining oxidation state? The first one is that any uncombined element is going to have an oxidation state of 0, or an oxidation number of 0. So if you have carbon, oxygen, gas, the elemental oxygen, sodium, metal, any of these would have an oxidation number equal to 0, or we say it has a 0 oxidation state. Okay, so that one's pretty simple enough. If we happen to have an ion, then what happens is that the oxidation state of the ion will be equal to its charge. So, chromium 3 plus has a +3 oxidation state. And if we have a negative ion like, iodide, then this would have a -1 oxidation state. Okay, so a monatomic ion is one, from the name. It has a single atom. Okay, we'll get to polyatomic ions, just a bit here. Now, let's go from talking about atoms and just single ions to talking about compounds, because really most of the time that's what we're going to be interested in doing. And so what follows are the rules for how to assign oxidation numbers for atoms that are actually within a compound. So the oxidation state of fluorine in a compound, fluorine will always have a -1 oxidation state in any compound that it's in. Okay, that's going to be an always true type thing. So if you have something like CH3F, that fluorine in that compound will have an oxidation state of -1. Okay, so that one's fairly simple enough. For oxygens in compounds, the oxidation state of oxygen is usually -2 in its compounds. The exceptions are the peroxides, where the oxidation state would be -1. So if we have something like water, good old water, in water the oxidation state of oxygen would be -2. Okay. However, if we have something like potassium peroxide, then this would have an oxidation state of -1. Okay, the peroxides, we don't see a lot of them. They are a little bit unusual, but it's an exception that you need to know. But almost always, the oxidation state of oxygen when it's in a compound will be -2. But once again, you gotta watch out for that, because oxygen could be an element, in which case the oxidation state is 0. the ion oxide is O2 minus, and then an ionic compound, it'll have a -2 oxidation state. For hydrogen, the oxidation state is +1 in covalent compounds and -1 in ionic compounds. So for hydrogen peroxide, here the oxidation state of hydrogen would be +1. Okay, the oxidation state of oxygen, because it is in the peroxide form, would be -1 in this case. If we have an ionic compound like lithium hydride, okay, the lithium would have a +1 oxidation state because that's the +1 ion of lithium, and the hydride ion has -1 charge, and so we assign it a -1 oxidation state in ionic compounds. So look for those metals, guys. If you see a metal and hydrogen is the anion of that metal, then its oxidation state will be -1. If, however, hydrogen is just in a covalent compound, you don't see a metal, you don't see ammonium, then the oxidation state of hydrogen would be +1. Alright, so from above you can kind of deduce this next rule, looking at the peroxide and the water. But it turns out that if a element, it's not hydrogen, it's not oxygen, it's not fluorine, we'll need to kind of back calculate what its oxidation state is going to be. So what we say is that in a neutral compound, the oxidation states of all the atoms need to add up to be 0. And for a polyatomic ion, the sum must equal the charge on the ion. So if we have something like CH4 gas, methane gas, we know from the above rule, Rule 5, that hydrogen has a +1 oxidation state because it's in a covalent compound. The whole thing has to be neutral though, so we have 4 +1 hydrogens, which gives us a total of +4, which means that the carbon then needs to have an oxidation state of -4 in order to be a neutral, in order to have a neutral compound to add to be 0. So if you add these two together, you get 0, and we get this nice neutral charge, as it were, for the methane. However, if we have a polyatomic ion like PO43-, oxygen would have a -2 oxidation state. We have 4 of them, which gives us -8. Now we want the charges, or the oxidation states rather, to add up to be the charge on the polyatomic ion. So we want whatever oxidation state phosphorus has when added to the oxygen oxidation states has to be -3. Okay, so this, we're not looking for a neutral compound. It won't be +8. Instead, what it will be is it will be +5. Okay, because if we have -8 +5 because of the oxidation state of phosphorus, then we get a -3, and that is the charge of the polyatomic ion. Okay, so anything that's not hydrogen, oxygen, or fluorine, you're going to have to kind of back calculate to find out what the oxidation state of that atom is in the compound. And again, this is just an accounting system. For covalent compounds, these don't represent actual charges on these atoms. Obviously, for our ionic compounds, the ions do have charges, and so the oxidation state is equal to the charge in the ion. So here's some practice for you, just to see if you've got it. Look at these 3 compounds and assign oxidation numbers to each of the atoms in those compounds. And go ahead, you can pause the video at this point, figure it out, and then we will go through it. Alright, so looking at this, I would say that each of these oxygens is -2. Okay, I know the sodium is +1 because it's an ion, so each of these will be +1. And then I need to figure out the sulfur. So you could do this a couple ways. You could say that it's a neutral compound if you have all this together. So you would have 2 sodiums plus 4 of those oxygens. So we have -8 plus 2 is -6. Okay. Therefore, the sulfur oxidation state has to be +6. The other way that you could do that is saying sulfate has a -2 charge, and then just doing it from that viewpoint, saying this for oxygen says -8, so sulfur must have a +6 charge to give me a -2 charge on the sulfate. For the NH3, each of these hydrogens is +1. We have 3 of them, and therefore this nitrogen would be -3. Okay, it's a neutral compound, so it all has to add up to be 0. And then for manganese phosphate, the 7 doesn't, the 7 is kind of a tip off here, because remember that our crisscross rule, that this 7 would be the charge of the manganese ion. So we can say just from that the charge on the manganese, the oxidation state of the manganese is +7. Okay. Phosphate, we have these 4 oxygens, which are -2. Again, you have a choice here as far as how you want to play this. You can say we have 3 + 7 manganese ions plus, let's see, we have +28, we have -2 oxygen ions. So we have 21 plus negative, let's see, 56, sorry, which gives us -35, okay, and then recall that we have 7 phosphates. Okay, so you just divide that 35 by 7. We need it to be neutral, so I should say we have, these 7 phosphates have to be +35. So divide that 35 by 7. So each of these phosphates would have an oxidation state of +5. Okay. And the other thing that you could do is think of it in terms of phosphate, as we did, in the previous slide. Think of it as phosphate has to have a -3 charge, and we have that -8 total from those oxygens, so we need +5 in order to get a -3 charge on the phosphate. Okay, and that is how you do oxidation numbers.